What is the difference between boiling and evaporating? Right, for boiling, it only happens at a specific temperature. And there will be some bubbling. So there could be bubbling, there could be bubbles. And the third one is that it needs energy. For evaporating, it happens at any temperature. It happens at any temperature. Now bubbling, here if it's boiling, it could be bubbling from the bottom. But here, evaporating is from the surface of the liquid. So B, at the surface. And for C, it doesn't require energy, because the one that has the atoms, the particles that have the highest energy will escape the surface. So those are the differences between boiling and evaporating. So boiling occurs at a specific temperature, and there could be bubbles, and it would require energy for boiling. For evaporating, it occurs at any temperature, and it occurs on the surface of the liquid, and the particles with the highest energy will escape the surface. We're going to be talking about internal energy and solids, liquids, gases, electric potential energy. We're going to be talking about Brownian motion, changes of state, and absolute temperature. All right, so let's talk about the three phases of matter, the main ones. Okay, so the three phases of matter, we have a solid, where it is a regular structure. They have a very strong bond. So solid is a regular lattice, close together, strong forces of attraction. They vibrate about their positions. So number one, they vibrate about their positions. It has regular lattice. They're close together, strong forces of attraction. So strong forces of attraction. Okay, so they vibrate. So this is a solid. It will vibrate about its own position, but it doesn't actually move. So it's not like a liquid. So let's just say that this is one of the atoms, and supposing like this is a spring, so it will vibrate about its position. So here, let's just say that's a spring. So this is the atom. It would only vibrate about its own position. It doesn't freely move. It's not freely moving. It's only vibrating about its position. So it's still fixed. So it can only vibrate about its own position. It has a regular lattice close together. It has a strong force of attraction. So that is the solid one. And what about a liquid? Okay, so the liquid is constantly moving. Now, for the liquid, they are still touching. If they weren't touching, it would be a gas. So, although it is not regular, if you think about, so this is a solid ice, and this is melting. It was, I mean, the atoms are still in contact with each other. So they're still touching each, so the atoms are still molecules, atoms. Okay, they're still touching, they're still in contact, they're still together. However, what they do is that it's constantly moving and they're free to move past each other. So it is constantly moving. It's moving past each other. So it's moving past each other, and it's weaker than solids and irregular. So it has a weaker force of attraction compared with solids. Weaker force of attraction compared with solids, and it is not regular, so it is irregular. Okay, so this is for liquid. It is not regular, meaning the atoms can slide past each other, moving past each other. Although they are still touching, they're constantly moving, and the forces of attraction is weaker compared to a solid. And what about a gas? Gas. Now, the gas, you've got these particles. Gas, the atoms are not touching, so they're far apart. They're free to move, random motion. So number one, they are far apart. They are free to move, So it is free to move, very random. It's very random. And for an ideal gas, there are no forces of attraction. So no forces of attraction for an ideal gas. It's very random, free to move, and they are far apart. What is Brownian motion? Now, we first found out Brownian motion from pollen and water. So let's just say that these are water molecules. These are water molecules. So those are water molecules. And then you've got some pollen. So the blue mark is the pollen, the shaded one. And the circles that are not filled in would be the water, let's just say. Now the pollen will collide with the water. So it will collide with the water. It might go there, it might hit that, might hit there, and this pollen might hit that one there, hit there, hit there. For example, so Brownian motion is the motion of the pollen going through water, and it is a zigzag random motion of particles in any fluid. So the pollen, the shaded circles, they're hitting the water molecules. And what happens is that they collide with the water molecules and it goes in a zigzag random pattern as it goes through the fluid. So Brownian motion is random motion of the particles in any fluid or even suspended in the fluid. What is internal energy? Right, supposing you have a liquid. So this is a liquid. Now, although this is not regular, so this, let's just say that this is a liquid. Now, these atoms or molecules will have kinetic energy. It will have kinetic energy. And it would also have potential energy. Now, the potential energy is because of the half mv squared. The potential energy is the interaction between the particles. So between particles, and that is due to the distance between each other. So this is internal energy. Well, that's the definition of internal energy. So the internal energy is the sum. So the internal energy is the sum of the kinetic energies and the potential energies. And these are all random. So that is the definition of internal energy. It's the sum of the random distributions. I'll write down the word random distributions. So it's the sum of the random distributions of the kinetic energy and potential energies of the molecules in the system. with the molecules. So it's the sum of the random distributions of kinetic energy and potential energy of the molecules in the system. All right, so that is the definition of internal energy. Now, what happens when you heat up a substance? What happens to the internal energy? Now, if the internal energy is the kinetic energy plus the potential energy, right, and you're heating it up, if you're heating it up, what happens to the kinetic energy? That will increase. So overall, the internal energy will increase. Overall, internal energy will increase. If you increase the temperature, as in if you're heating it up, the kinetic energy will increase, the temperature will increase, and therefore the overall internal energy will increase. Let's talk about the internal energies of a gas, liquid, and a solid. Now, an ideal gas does not have potential energy. So let's just say that this is a gas. Why does it not have potential energy? Now, the reason why it does not have potential energy is because there is no electrostatic forces. So for a gas, there is no electrostatic potential energy because there are no electrical forces. They are very far apart. So far apart, there are no electrical forces, so there's no electrostatic forces. So there is zero electrical potential energy. So number one, it is far apart. Number two, there are no electrostatic forces. This is for an ideal gas. And the third point, because of those points, you assume that it has zero electrical potential energy. And what about the change of state? So when it changes states, let's just say, for example, from a solid to a liquid, what you're doing is that you're giving energy into the solid. So changing state so from a solid to a liquid, what are you doing? You're giving energy into it. So energy is going into the solid. The energy is going into the solid. Now, because it's changing state, the kinetic energy stays the same. So it stays the same. However, what is potential energy? Potential energy is because of the forces between the molecules or the forces between the particles. So the potential energy is due to the forces between particles. And when you're adding energy to the solid, so let's just say that this is the solid ice. You're adding energy into it. So you're adding, this is a Bunsen burner. So heat. Now the kinetic energy stays the same, so you're putting energy into the bonds. So the energy is put into bonds to be broken, So now the electrical potential energy has gone up, and the kinetic energy has stayed the same, 0. So overall, the internal energy has gone up. So that's the electrical potential energy has increased, but the kinetic energy stays the same. So the temperature stays the same. The temperature stays the same. The kinetic energy stays the same. But because you're putting energy into the bonds to be broken, the electrical potential energy has increased. So this has become, so this was very negative, wasn't it? So this is very negative. And now it has become, it's more positive. So this is very negative. So this is just negative. Let's talk about absolute temperature, the absolute scale. So the absolute scale is Kelvin, and 0 Kelvin is where it is the most minimum internal energy. Now, kinetic energy is related to temperature, isn't it? So temperature is related to kinetic energy. So the higher the kinetic energy, the higher the temperature. And there is a relationship between kinetic energy and temperature. So what happens at 0 Kelvin? So when it's at 0 Kelvin, theoretically, is where it's 0 kinetic energy, theoretically. Theoretically, so when it's at 0 Kelvin, it is minimum internal energy. It's where the particles are theoretically not moving, they're still, but in practice it is moving very, 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 very slightly, because it is very, very impossible to get to 0 Kelvin. That's the third law of thermodynamics. It is impossible to reach 0 Kelvin because it is impossible to have 0 potential energy and 0 kinetic energy. But theoretically, that's what it means. When it's at 0 Kelvin, there is 0 kinetic energy. And what is the conversion? Now, the conversion between, is it 273? How do you convert to Kelvin? So Kelvin is Celsius plus 273. So Kelvin is Celsius plus 273. So when it is at 0 Kelvin, Celsius is minus 273 degrees C.